Hi there. This video is going to talk about entropy and Gibbs free energy. So first I'm going to talk about entropy, and then we got Gibbs going on later on. So let's get started. All right. I personally love the topic of entropy. Entropy is this idea that I feel like my world is always in. It's this idea of it's random. Everything like turns to chaos. Don't you feel like that happens on some of your days? So entropy is represented by the letter S. First thing to kind of know. Every thing has a symbol, right? So entropy is S. And it can be thought as that measure of randomness. And so when we're talking about randomness or how much chaos there is, that is entropy. What we're going to talk about is entropy in just a certain situations. For example, the most easily understood one is looking at water. Like if we have water as an ice cube, here it is as an ice cube, they're stacked up so nicely. They're set in their perfect little intermolecular forces. They've got their attractions to the water next to each other. They have this kind of honeycomb shape. They are very well ordered. There's not a lot of entropy there, not a lot of chaos. Once you add a little bit of heat and it starts to melt, you can see that things can kind of go wherever they want, right? They're still attracted, the water is, but it's a little more random. It has more entropy. Now take our liquid and take it over to a vapor. And when we're looking at a vapor, our S, or entropy, is going to be greater at that state because all of the gases get to go wherever they want. That's a lot more chaos, a lot more random. It has a higher entropy to it. So when we're talking about entropy, we're really looking at the signs, meaning we want to look at through the change. So if things become more random or more chaotic, it'll be a positive S, an increase in entropy. So I'm using the word chaos. That's what I tend to think of in my world. More random, more chaos. If it is less random, more ordered, then you're going to get a change in S that's going to be a negative value. So this kind of relates it back to the H's, the enthalpies. When it's a negative H, that means it's exothermic, it releases heat. A positive H means you're putting in heat. So this is our entropy one. Positive as S, more chaos. Negative S, less chaos, more order. Okay, so I'm going to take you through a couple examples here and see how we do. Let's say you take solid water and it sublimes into gas. What that means is we're taking a solid, it's a crystal structure here of ice, and it goes straight into the vapor state. This happens in your freezers. The ice cubes suddenly are smaller than when you first put them in because it's subliming, going from a solid to a gas, or dry ice does it too. So I know when that happens, there's a lot more chaos. It's going from a structured system to a chaos system. More chaos means more entropy. That's a positive S. Take a look at this one. Water at 42 degrees changes to water at 66 degrees. Well, when I think about that, that's just a temperature change. And when the temperature has increased, that means they're moving faster. And when everything's moving faster, it makes me think of like a bunch of like children running around a room or walking around a room. There's a lot more chaos with children running around the room. So when you've got a faster moving water molecules, yes, it's still water, you're going to have more chaos. More chaos, positive S. Taking a look at this example, we're going to get a little bit trickier here. Here I've got 2NO plus O2, and it does a reaction and becomes 2NO2. Now when I look at it, I first want to pay attention to the fact that they're all gases. So if one was solid and one was a gas, that would automatically tell me that which one's more chaotic. But here I have all gases. But the difference is how many gases I have. Here, I happen to have 3 moles of gas. I know that because there's 2 NOs and 1 O2. 2 plus 1 makes 3. 3 moles of gas. Over here, I only have 2 moles of gas. To have something where there's 3 moles of gas, that's a lot more chaotic than 2 moles of gas. It's like 30 people versus 20 people. 20 people can be a lot more 20 people will be more ordered. 30 people are a lot more chaos. So as the reaction goes on, I get fewer, we'll say people in the room, or in this case, gas, and that would mean things are more ordered. They're a little less chaos, more ordered. More ordered is a negative S. Why don't you hit pause here and you try these ones, plus S or minus S, and then come back and see how you did. You could skip past my reasoning and just go straight to my answers and then go back if you need to hear my words. All right, so when I look at this, what I see is it's water going to water, but it's going from a liquid to a gas. Liquid to a gas means it's becoming more chaotic. Gas is way more chaotic. That's a plus S. Number 2, when I'm taking a look at this, it's a reaction going on. I want to take a look at my solids. Solid versus gases really tells me the big difference about chaotic. Like a solid is structured, it's set in this one little spot. Gases can go like anywhere. It's way crazy. So when I look at this one, I can see that on the left side, my reactants, This one has a gas. That's a lot of chaos compared to going to the product side, which has a solid. Going from a gas to something that's a solid is going to create more order. This is a negative S situation, more order. And the last one, they're both at 25 degrees, but I got 2 moles versus 1 mole. Same substance, add a gas. 2 moles is going to be a lot more chaotic than 1 mole because there's a lot more stuff. There's a lot more options on how it could be arranged, a lot more chaos happening. So 2 moles to 1 mole, I'd have to say this is a negative S. It's becoming more ordered. All right, moving on to the next big thing about entropy. So hopefully this equation looks kind of familiar to you. It looks just like the one you do for enthalpy when you're doing heats of formation if you're going through all this. Same idea here. You can look up tables of how much chaos is in each of the substances at their state of matter, as you can see. What really happens when they're looking at how much chaos is in like a molecule, like if you have a set molecule, and let's say it's got a bonds like this, like 2 atoms are bonded together, they can move by going like in and out, in and out. They can move by going side to side, side to side, and they can spin. And so they look at all these molecules and they see how many different microstates is what they're technically called, but how many ways can it spin or move or be chaotic? So that's my general idea here. And we give it a number, or actually we can calculate the number. And then we can use those numbers to figure out as the reaction goes on, if it's not obvious, is it more chaotic or is it more ordered? And so I'm going to show you how to do that on this next example here. Okay, so calculate the change in standard entropy of the system, change in S. So it's kind of like it's trying to find the change in S of the reaction over here. For the synthesis, that means production or combination or making of ammonia, which is NH3, from N2 and H2. One thing to notice here is that all compounds will have an entropy number. This doesn't have anything with zeros because everything has its sort of random. Like even if you take an atom, the electrons have a sort of randomness to them inside there, and the protons, they are trying to hold it in state, but electrons get to go wherever they want. So everything has entropy. No, nothing's at zero. So bringing it up here to the equation, we're going to find the change in S, meaning change in entropy of the reaction. Rxn is usually the symbol for reaction, as we take the products minus the reactants. And this little e thing means the summation of. So we're going to sum up or add up all the products, all the s's of the products, and subtract it from adding up, here's another summing up all the s's of the reactants. Okay, so change in S equals summation of the products minus the summation of the s's reactants. Kind of hard to write on the screen, sorry. Change in S equals, let's take our products here. I only have NH3. NH3 is 192.5. Now I happen to have 2 NH3s. Notice that 2 right there. So I do need to multiply this by 2 because we have to add up all of the products. And that happens to include 2 NH3s. So there's my products minus all of my reactants. Hope I can fit it in there. One of my reactants is N2 as a gas. So 191.5 plus, I've got to add up my hydrogen. Hydrogen is 130.6. And remember, I have to include all of them. There happens to be 1 nitrogen, so I'm good there. But there are 3 hydrogens. So I've got to take this number and multiply it by 3. And now I'm just going to push buttons in my calculator. I'm going to hit pause so you don't have to wait for me to push buttons. All right, magic of the video. I pushed the buttons in my calculator. If I pushed them right, which I hope I did, negative 390.8. Oops, sorry, not kilojoules. That was the heat one. Joules per Kelvin. Entropy is always dependent on temperature, and that kind of makes sense because you can think like if it's at a higher temperature, you're going to have a lot more chaos. So we do have it per Kelvin kind of system. That would be how I calculate the standard entropy. Here's a question that asks you to do the same thing. And so I'm going to have you do it. My next slide actually gives you the answer. So you've got a sample of this big stuff, which is this, is placed in an insulated container where it decomposes, that means breaks apart, into ethene and ammonia, according to the reaction represented above. Boom. They actually give you those numbers down here. And your job is to calculate the change in entropy, or the standard entropy change, just like we did. So change in S. So that's when you're going to look at the summation of the products minus the summation of the reactants, just like we did in the problem above. So hit pause, give it a try, and then hit start. Here's the answer. And all the work is in there too. So hit pause if you need to, because I'm going to go forward. All right. Here's another great place to hit pause because if you love Calvin and Hobbes like I do, I think this one's hilarious. But we're going to talk about Gibbs free energy. That's the last kind of thing in this chapter. And Gibbs free energy allows us to know if things are spontaneous or not. And so the letter we're dealing with now is G. We'll get back to that G. So what that means is, like, a lot of the labs that you're going to be doing, you put two things together and magically the reaction happens and it's awesome. That would be a spontaneous process, something that happens once it's started, once it's initiated, it'll actually happen. So spontaneous does not mean it happens fast. It just means it does happen. Um, like rusting. If something rusts, it doesn't necessarily happen very fast, but once you expose it to water and air, that metal is going to rust no matter what you do. So that would be a spontaneous process, rusting of metal. All the reactions that we do in the labs is going to be a spontaneous process because we want it to happen. We want to see the results. A non-spontaneous reaction would be something where you have to put an input. For example, if I wanted to run a fan, I'd have to plug it in to the wall to run the fan. That's a non-spontaneous reaction. If I just have the fan sitting there, it's not actually going to happen. I have to provide energy to make it happen. In a spontaneous process, the reaction happens and it's kind of providing energy out. Like when we talk about redox reactions, we're going to produce a battery that can produce electricity, and that electricity can go out into the world and do things with it. Spontaneous reactions do that. Non-spontaneous reactions mean you have to put energy in, like maybe in the form of electricity, to make the reaction happen that otherwise wouldn't want to happen. Yep, that's where I'm gonna leave it with that. So when we're dealing with Gibbs free energy, that's this G thing right here. And we can calculate that standard free energy. Standard is what this little circle thing means. That means standard. So if I wanted to calculate it, you can see this reaction looks totally like the S one we just did, and it looks totally like the H one, and that's true. We can have little tables that have a bunch of H's on it, and a table that we can look up all the free energies of all the compounds in the world. And so you can use these values to actually find the free energy of a reaction if you should need so. So I'm not going to do a problem like this, but you can see it's exactly the same, where I'm looking at all the products added together in a reaction minus all the reactants added together in a reaction, just like the S ones you did. The new thing here is that we can actually put all these letters together. So here's Gibbs free energy. That's this G thing. Here's H. This is a reminder as is enthalpy. That's that heat thing. So if enthalpy is negative, you're producing heat. Enthalpy is positive, you need heat to go in. T stands for temperature, and it has to be in the Kelvin system. Otherwise, you're going to be left with negative values, and that's just not possible in any of the math that you do in Chem. S right here, that is our change in entropy, which we just covered. Okay. Oh, okay. This is why I'm going to do the math for you. So why we need this equation is if we want to know if something's spontaneous, like if I put the compounds together, will the magic happen? And we can calculate that by looking at Gibbs free energy. It's this balance between enthalpy, how much heat you need to put in, and entropy. That the idea that the world, everything wants to go to chaos. That's the law of thermodynamics, not thermodynamics, but the law of the universe would be everything wants to go to chaos. And if you look at, well, everything, the pyramids, anything in people's lives, I feel like everything does kind of go to chaos, right? So the change in G, if we find the change in G when we push in buttons and push in numbers, which I'm going to do next, is a negative number, then the reaction will happen spontaneous. Means put compounds together, magic will happen. I'm not saying fast, but it will on its own happen. If you do all the calculations, you get a positive number, then the reaction will not be spontaneous. That means if you want it to happen, you better add electricity or some sort of outside source of energy to make that happen. Okay, so let's do a little math here. Okay, remember you can look up the H of F, the formation values for any of your compounds. Here's my big old reaction. And if you actually calculate the H of F for this reaction, you'll get this number right here. And then if you want to use the heat of, not the heat of formation, but the entropy values and calculate it with that big equation that we did earlier, with all these numbers using this equation, you could totally get this number right here. That's what I did ahead of time to find it. What I'm doing in this slide is actually going to take these numbers and plug them in to find the G. So if I want to find the Gibbs free energy, in other words, I want to know, is this reaction spontaneous or not? Will it go on its own if I put the compounds together? Then I'm going to need to do change in H, 62 kilojoules per mole. That's my change in H, minus T. Let's say this is going to be at room temperature. So room temperature is about 22 degrees Celsius. And so in the Kelvin system, I've got to get 273 plus